So, hi, my name's Tom Olson. I work for ARM. I'm chair of the Vulkan Working Group. Today's talk, I'm the kickoff talk of our 3 hours of Vulkan sessions. I'm going to start with a very quick level set on Vulkan. I'm going to spend half my time talking about what's new in Vulkan, various topics, particularly over the past year. And then I'm going to spend the rest of my time talking about what's next for Vulkan. So if you didn't know, in which case, what are you doing here? But whatever. So Vulkan is an API for graphics and compute on GPUs. It's based on OpenGL and OpenGLES, distantly descended, and it's cross-platform. Our goal is to make it available everywhere. Today it supports devices ranging from embedded and mobile up to desktops and servers with a single API. Vulkan prioritizes performance over almost everything else, certainly including ease of use. It does that because that's what its core constituency, AAA game developers, asked for, and their needs were primary in the design. A result of this philosophy is that Vulkan makes the programmer responsible for a ton of stuff that the API used to do for you in the old days. That includes object and memory management, synchronization, thread management, and even error checking. It demands a lot of the programmer, but it gives you in return the opportunity, though not a guarantee, of the best possible performance. Since launch in 2016, Vulkan has been widely adopted. There were implementations available from all of the mainstream GPU vendors except Apple. At the platform, they are a mainstream GPU vendor. At the platform level, it's available on Windows, Linux, Android, several game platforms, including Switch and Steambox. And although it is not officially supported on Apple, you can write Vulkan applications that run on Apple using the Molten VK shim layer. And finally, of course, tons of middleware. All the big game engines have Vulkan paths. Vulkan is used for all sorts of performance-sensitive applications, games, obviously, both desktop and mobile, but it's also used in applications as diverse as video editing and effects, various kinds of artist tools, real-time event visualization and control, and scientific visualization. Basically, any graphics application that has a real-time element and/or needs to make maximally efficient use of CPU and GPU and/or needs to run cross-platform can potentially benefit from using Vulkan. Historically, we started thinking about a successor to Vulkan, to OpenGL in 2012, but we didn't really start working on it seriously until 2014. We announced that effort here, kind of, at SIGGRAPH 2014, and then shipped version 1.0 at the beginning of 2016. It succeeded beyond our wildest dreams, and we've been working like crazy ever since to keep up. Our methodology is we develop all new functionality as extensions, and when the time comes to release a new core spec, we promote the extensions that we agree are appropriate into that. And we've done that every 2 years since 2016. In 2022, along with Vulkan 1.3, we also introduced a profile system and the beginnings of a formal roadmap. That activity is now central to how we plan to move forward, so I'll say more about it at the end of my talk. So enough history. What's new? As I said, Vulkan is not supported on Apple, but it has been available on Apple platforms for quite a while. You use it by linking your application with the Molten VK library from Brenwell Group, which translates your Vulkan calls into Metal. What's new this year is that Molten VK is now caught up to Vulkan 1.2, only one version behind. It's still a subset, so it's not a conformant implementation, but it's a very well-defined and well-tested subset. It's relatively easy, using tools provided in the SDK, to write applications which stay within that subset and will run fine on Mac. The performance of the Molten VK shim library is also extraordinarily good. And as a result, tons of apps are using it, including big commercially important applications like Autodesk Fusion 360, Dota 2 in the game space, and a ton of other games, and a lot of very interesting middleware. In the Android space, I don't have current numbers. These are from January. But in January, Vulkan was on 85% of active devices visiting the Play Store. I would guess that it's above 90% now, based on the curve, which, as you can see, is pretty linear. We're approaching the point where, in my view, maintaining a separate path for non-Vulkan devices is beginning to be a questionable value proposition. So that's exciting. Functionality. As usual, kind of the bread and butter of working in the Kronos, in the Vulkan Working Group, is adding new features to the API through extension. This is what we've done in the past year. I tried to categorize them in terms of the rough area of functionality, but I caution that these are my categories. If I say something's experimental, there might be other people in the working group who disagree with me, but this is the best I can do. I'm not going to obviously try to talk about all of these, but I want to highlight 3 of the subgroups within this space. First of all, Vulkan Video. This was originally released more than a year ago as a set of 7 provisional extensions. Provisional meaning they're not final and you aren't supposed to put them in production code. The decode side of the stack has now gone final and been released, and it's starting to see serious adoption. It's used in FFmpeg, the latest version, and therefore it's being used in some of the applications that use it, such as the MPV media player. There's work ongoing to use it in GStreamer, although that's still in pull requests. Several Mesa drivers, including ANV and RADV, are close to having shipping implementations. And the TSG is now working, now focusing on getting the encode side together and on adding more codecs like VP9. Tile-based optimizations. So back in OpenGL, we had a number of extensions that exposed the ability of tile-based GPUs to read from the frame buffer in a fragment shader and see values written by previous fragment shader invocations at the same pixel without generating a ton of memory traffic, or any indeed, and without causing huge pipeline bubbles. This is very useful for things like deferred shading. Vulkan had a subpass mechanism, subpass dependency mechanism, which was supposed to give you the same functionality, but it turned out to be hard to use. Developers didn't like it and found it just generally awkward. So a year ago, we released an extension called Rasterization Order Attachment Access, which gives you the equivalent of GLES frame buffer fetch. It's basically comparable functionality, but significantly easier to use if you're willing to have your code actually admit that that's what it's trying to do. A problem with that extension is that it built on subpasses, which meant that you could not use it with dynamic rendering, which is our latest preferred formulation for writing render loops. So this year, we've released a new extension. Whoops, sorry. How do I back up? There we go. We have a new extension, Shader Tile Image. It's basically the same functionality, but it works with dynamic rendering. So that means that when this is fully adopted, which will be a while, I don't believe it's shipping anywhere yet, but when it is available, you'll be able to move to dynamic rendering completely and get rid of subpass dependencies and multiple subpasses entirely. At the same time, you'll still get the memory bandwidth benefits on tiled architectures. Finally, one of Vulkan developers' least favorite experiences, SIGGRAPH, you have to have an explosion somewhere, is getting device lost, which typically means the GPU hit a memory fault and the driver is now dead, and you can no longer talk to it. These errors are very hard to debug because state is completely lost. You have basically no visibility into what happened. A few years ago, we set out to create a family of extensions to help with this problem. That was a special effort led by Ralph Potter of Samsung. We've now released 2 extensions that we hope will help from that effort. ext device fault lets you, after a device lost, you can now talk to the driver a little bit. You can ask it what went wrong. What you get back will be implementation dependent, but it might be something like, I tried to do a storage buffer write at this address and I died. So once you have that, well, you know more than you did. And if device address binding report is also supported, that gives you tools for tracking how regions of address space are bound to Vulkan objects. So you might be able to find out that the address that device fault told you you faulted on was bound to a particular buffer object, but that buffer object had been freed, in which case you're doing a classic access after deletion. No wonder you got in trouble. That's a best case, but these are tools that we hope will help. We have other things in mind. We're working on a progress marker type extension, which you may be familiar with. We don't have those yet. These extensions are, I believe, also not supported anywhere yet, but support is coming. Our DevRel effort is led by Marty Johnson, who used to run DevRel at AMD and is now doing it part-time for Vulkan, as well as helping me with working group project management. He works with Tim Lewis in Kronos's marketing department, and they, together with Steve Winston of Holochip, are leading several efforts to improve our documentation and our developer outreach. One of those projects is Vulkanize 2023. We've done full-day developer events in the past, but this was taking it to the next level. This was a 3-day conference in Munich, Germany. Open call for papers, 180 people attending. And about half of the program were presentations from outside Kronos, a mix of academia and industry. People who were there said it was terrific and that we should do it again, so we're going to try. Currently planning, I think I can say, should be February 24 in the Bay Area. All a little TBD, but that's where we are, and the call for papers should be out in a couple of weeks. Kronos provides a lot of documentation and developer information about Vulkan, but it's kind of scattered all over the place and hard to navigate. We have a project to try to bring it together, present it through a common user interface with cross-link capability and searchability. That is work in progress. We're not there yet, but there is a proof of concept prototype. Sorry, I don't have a nice QR code. I just have a URL. But if you search for it, Vulkan Documentation Project Demo, I think you'll be able to find it. We would love feedback on this. Do you think this is a good idea? We're currently saying, okay, what's next? We have a proof of concept. How do we make this complete? And we would love feedback and suggestions. Another project we'd like feedback on is procedural valid usage statements. If you used Vulkan, you know the spec is littered with blocks of text like this. These are valid usage statements that tell you all the things your app has to do to use the API correctly. If you break those rules, undefined behavior, anything can go wrong. Those rules are currently written in English, which is not good. It's a manual process. Translating it into validation layer software is a manual process, and because it's English, it may be ambiguous. So Shabazz Yousefi of Google had this idea, what about if we write these in code instead of in English? He's done, again, a proof of concept, which is, I believe, not exposed on the web, but we've been looking at it. This is not a good example because this valid usage statement is very sensible, but they get a lot worse. And sometimes code is significantly easier to read. It also, because it's code, you can imagine doing all sorts of interesting machine-readable things like auto-generation, CI checking, etc. We don't know if we're going to do this for real. We've basically come to a decision point. We're now looking for feedback. Is this something you'd like to see us put resources into? So again, there is a proposal on the Vulkan docs, which is the specification repo, and it includes the Python language and the sort of the interface to it. If you have time and interest, take a look, give us feedback. We'd love to have that. SDK, well, I'm not going to say hardly anything about the SDK because Karen runs the team that builds it, and she's going to do a better job than I would. But I did want to brag about one thing. The Windows SDK is up to 35,000 downloads a week. That just blows my mind. But Karen will cover the rest. One more thing in terms of what's new is actually not new, profiles. We introduced these at the beginning of 2022 along with Vulkan 1.3 as part of an attempt to deal with the fragmentation problem in Vulkan, or to give you tools to manage it. I talked about them then, but we haven't said anything since, and I feel like when I introduced them, I didn't really make the case for how awesome they actually are. So I'm going to try again to convince you that profiles are awesome. So hopefully you know, Vulkan defines a huge number of optional features. Extensions are optional by definition, of course, but even within a core spec or within an extension, there are features, capabilities, format features, all kinds of things which may or may not be supported. So when your app starts up, it has to query the core version, the extensions, and a huge long list of Boolean flags that tell you what features are really supported. Then you have to query numeric properties like how many render targets can I have, how big can they be, what pixel formats can I use, which ones can I render to, all kinds of things which are not, you know, the answer to those questions is not in the spec, it's in your implementation. Then your application has to decide what to do with that information. This is a huge pain, and it makes writing portable applications hard. Unfortunately, we can't fix that problem. It has to be this way. Vulkan runs on devices that will fit in a wristwatch. It runs on devices that fit in 4-card SLI AFR systems where each GPU has its own power supply and everything in between. And you cannot logically expect them all to support the same feature set. So optional functionality in core specs is just a fact of life. Fortunately, it's not quite as bad as I make it sound. It's not the case that every GPU supports a different, completely random collection of extensions and features. There are islands of coherence within markets. Mobile devices tend to have similar functionality. Things that support DX12 obviously have similar functionality. What we need is a way to make those regularities explicit. Enter profiles. So what's a profile? A profile is a formal specification of minimum capabilities across a family of conformant Vulkan implementations. It defines a subset of the space of possible implementations that supports at least a particular core version, a particular set of extensions, at least a particular set of features, etc. Implementations in that subset may support more than the profile calls for, but they may not support less and call themselves conformant to the profile. Whoops. Profiles depend on a core spec, but they are not part of the spec. The spec doesn't know that profiles exist. We define tools for working with them, but they're in the SDK, not in the API. Whether a profile is supported depends only on the API version number and the extensions, features, and limits and formats exposed by the implementation, which means that you can write a new profile that describes old devices. Profiles are specified using a JSON schema. Here's a picture of one of the Android baseline profiles. So they're human readable, but they're really meant to be read by machines. This enables all kinds of interesting code gen and magic, as Karen will talk about in her presentation. Profiles are a simple idea when you think about it, and they seem kind of obvious, so it would be easy to miss how awesome they are, as I did. Here's why I think they're awesome. First, if you've got a profile that meets your needs, it's like having your own personal Vulkan core spec. It supports all the features you need. It supports all your favorite extensions. It isn't on all devices, but no core version other than 1.0 is on all devices, so that's not really a loss. As long as you code to use only the features that are required in the profile and target devices the profile covers, it's just as good as a core spec. Actually, it's better. It's better because, think about it, if we released Vulkan 1.4 today and it had all your favorite features and all your favorite extensions in it, you still couldn't use it because it wouldn't be on any devices. New core specs take time to work out into the market. Profiles describe existing stuff or potentially existing stuff. And so, you know, if there are devices out there that support the profile that you like, even if the profile has just been released, you can start using it immediately. Another way it's better is that you can start using it with little or no change to your existing code. If you want to target a new core spec, you have to go through and change all the names, remove the suffixes from the promoted extensions. But you're not going to do that, are you? Because you wouldn't be able to run on old versions of Vulkan, and you wouldn't, and besides, there are no devices out there in the market that use the new core version. So to use a new profile, all you have to do, and this is optional, is add a query saying, is this profile supported? And then, if so, create me a device that supports this profile. And you've written this many lines of code, and you've got a device that has all the features enabled. And you can enable other features. We have backdoors. Again, Karen will talk about that. So that's awesome. To make it concrete, suppose you're writing an Android game. You're probably going to target devices as much as 4 years old, with a dozen GPUs from 4 different GPU vendors and a handful of handset OEMs. So you have a fragmentation problem. Now suppose Google says, here's a profile, target this, and you will be able to run on 90% of the devices that hit the Play Store in the last month. Seems like a win. And they've already done it. Android Baseline 2021, in January, 87% of devices, certainly at 90% now. Android Baseline 2022 is lower. I think it's at 80% of devices in January, but you know, progressing. So if you confine yourself to using the profile, you're not using every feature that all the devices support, but that's really hard to do. Your job will certainly be easier, and this is certainly a great place to start. 5 minutes? Okay. What's next? This is going to be 5 minutes. Let's talk about the future. When we released Vulkan 1.3, we set some ground rules for the future. We continue to release extensions as we always have, but we now have 2 different kinds of major releases. Core specs, what they've always been, are meant to be supported on all new devices going forward, and also to be backported to any device that can get a driver update that isn't at end of life. That means that core specs typically won't require new hardware features. They provide what we call quality of life enhancements, things that make the programming model better, but don't require new hardware. For example, synchronization 2, pipeline creation feedback, dynamic rendering, and no optional features in new core specs. That is, no new optional features. We can't get rid of the old ones. The other thing we'll release, the other spec we'll publish, is profiles. These describe the functionality you can expect in implementations aimed at specific market segments. And that's where you'll find requirements for new hardware features. Along with core and profile specs, we plan to maintain a formal roadmap. We're trying to accomplish 2 goals with this. One is to reduce fragmentation within a market segment. So in the short term, what we'll do is capture what's common to the market segment, but by publishing the spec, and it will be visible to GPU vendors long before it's published, we can encourage them to work toward a more coherent ecosystem and a larger common feature set. The other thing we want to do is enable ourselves to take a more coherent approach to long-term spec development. Develop specs like the crash debug, device loss debug, things that I talked about, families of specs that work coherently together to solve larger problems. In this new world, the working group is thinking about market segments. So you might ask, what market segment is your roadmap targeting? We call it immersive graphics, which I write in sneer quotes because it's so horrible. But what it means to me is, or it means to us, is mid to high-end devices, smartphone, laptop, console, desktop, which I translate to devices aimed at the consumer that support an active third-party software market for games and media applications. We could do other things. We have not currently decided to do that. So here's what we plan to deliver in the new flow. We started in January 2022 with Vulkan 1.3. That's where we adopted this new philosophy. Along with that, we released Roadmap 2022 as a profile, capturing functionality that we expect to see in immersive graphics devices starting in 2022. The criteria and the commitment we make is that every vendor within Kronos who targets the immersive graphics market has said we'll have a device, at least one device, that supports this profile in the market by the end of 2022-ish. Also, we agree that eventually these features will be universally supported in the immersive graphics market. At the start of 2024, we're now talking really about the future, we'll release the next roadmap node, Roadmap 24. This will again be a profile using the same criteria, making the same commitment, just moving everything forward 2 years in time. We don't plan to release a Vulkan 1.4 at the same time. We looked at the set of features that we could plausibly require in it that would be supportable, and it just didn't add up to a compelling product. Given the amount of work that it takes to absorb a new core version into the ecosystem, we agreed that it's better to wait. We certainly will do a Vulkan 1.4. It's a question of when we have enough pure quality of life features to justify pushing it out. Future roadmap profiles will follow on our usual 2-year cadence. I should say this is the plan, and we'll be watching closely and listening to you all for your feedback. If this turns out not to work well, we'll change it, but this is the plan. As I said, 2-year tick. I have just a little bit more to say. As part of our roadmap development process, we're trying to extend our planning horizon further into the future. We used to just finish Vulkan 1.2 and then start working on 1.3, and finish it and then start working on 1.4. Not good enough. We're trying to look as much as 5 years or more out into the future. So, Roadmap 2024, basically done and dusted. Content is frozen. I'm not going to tell you what's in it, but I will around the end of the year. So right now, as far as 24 is concerned, we're just doing packaging and support and dotting the I's and crossing the T's. But work on 2026 is well underway. We can't write Roadmap 2026 as a profile today because it's going to need extensions that we haven't written yet. So we're thinking in terms of problems that need to be solved, needs that need to be addressed. So we're defining it now in those terms. We'll use that information to guide our spec development process and the extensions that we write, prioritize the work that we do over the next year and a half, and then we'll eventually build a 2026 roadmap profile from that. I hope we'll be able to talk about our plans for Roadmap 2026 at the same time that we release the 2024 profile. Working group hasn't signed off on that yet, but that is the hope. And we're starting to sketch Roadmap 2028, which is about as far ahead as we can sanely think about. Our view that far out is hazy, but we are putting things into that bucket. Part of the reason we're doing this is that that's how far you have to go in order to have a prayer of influencing future hardware generations. And we want to be able to do that. Again, partly just to reduce fragmentation, and partly because we think we have ideas. We think we can accelerate the progress of the technology by doing that. Given that the goals of Roadmap 2026 are being defined now, this is a great time to communicate with us what you want to see from Vulkan as far out as 2028, but particularly 2026. You can do that by raising an issue at the spec repo. Don't be shy. It's just an issue. And we will look at everything. And that's probably the best way. It's long-lived. People can comment, etc. We do have a Discord channel that we monitor, and we still monitor Kronos Dev Slack if any of you are on that. And of course, you can talk to us at events like this. If you want to talk to me here or at the reception, you can't miss this shirt. I will be easy to find. I guarantee there will not be another person there wearing one like it. That's all I have. Thank you. Do we have question time or not? So, am I live? Yes. So while Neil and Karen get Karen's slides visible, if you have questions, I'm happy to take them.
Hi, I'm Alexei from Meta. I have actually 2 questions, 1 suggestion probably. So the question number 1, do you have any influence on Google with their profiles? And maybe any kind of recommendations that you can give them out for the Android devices? What exactly they need to support for profiles?
So it isn't for me to speak for Google about their process, so I'm being a little careful here. Google does, of course, talk, actually, Trevor can take that. Trevor can speak for Google if he's willing. Yeah.
Okay.
I will say Google is a very active member of the working group, and they're not shy about telling us what they think we need and vice versa.
Happy to hear your question. Context, I'm Trevor Black. I work on the Android part of Google, specifically representative for the Vulkan Working Group. I am somewhat responsible for the Android baseline profile, so I'm happy to hear any suggestions or comments you have.
Yeah, so basically the question is, well, we definitely want to make our life easier. And Android, to be honest, it's probably the biggest pain in the ass in general. And yeah, we just want to make sure to have like any ideas how you want to, I mean, like design the profiles. Are you going to change like every year or whatever? I mean, we definitely care about the coverage on one sense, and then we don't want to lose the features. I mean, what's your kind of rough idea how you want to drive this?
Sure. So if I were to repeat the question, it's kind of what's our plans? How do we want to evolve this moving forward?
Yeah, how you want to evolve this and maintain.
So as said in these slides by Tom here, we released a 2021 profile and a 2022 profile. We do not intend to release a 2023 profile. If you have an idea of the cadence you'd like to see, please tell me now or afterwards. We are slightly cautious at releasing something every year because we want to establish a stable platform for everyone to develop on, so that every year or every 6 months, what have you, a developer doesn't have to go, oh crap, there's more extensions and features that I need to worry about. So if you have a cadence you'd like to see us be at, we'd be happy to hear that. We will not be doing one this year. Moving forward, we're going to continue doing this. It's something we desperately believe is needed in the platform. It's why we're really pushing on this. So we have all the tools, we have all the analytics, and we're just trying to figure out at what cadence we're doing this at, and if there's any features or extensions that you think are really important for you and your platform, we'd also love that feedback, because we can then go to Tom and associated IHVs and say, hey, we know for a fact that Meta cares about this. So it's a little more open-ended than that, but does that make sense?
Yeah, absolutely. Thank you. And second one, this docs generation code actually looks pretty much awesome. I wonder if you can train ChatGPT basically to do the checks for us.
We should train ChatGPT to write the spec. That would be even better.
Oh, that's, yeah, then we can collaborate, I think. Yeah, thank you.
Right. Do we have time for another question, or how are we? Neil, I mean, depending on you to enforce. Okay.
Sure. I'm Vipul from Autodesk. This could be a little too specific of a question, so please let me know. In case of device lost extension, I suppose you're giving some context to what operation has caused the device to lose. Does that tie in with some debug marker support so I can actually figure out what buffer that I've annotated actually, caused the crash, for example?
So unfortunately, we talked when we were designing these, can we standardize the response you get? So really all you get from device fault is a query saying, give me the crash info. And you get a structure of records which have text fields in them and numeric fields. And What is in those is completely up to the vendor. You know, we just could not find a sensible way to, you know, to make it more standard than that. And of course, it's not at all intended for runtime decision-making by the application. It's really just to give the developer a clue about what they should be looking at. Yeah, there are many problems with these extensions. For example, conformance testing them. You can only test this code after a device lost, which we don't have a reliable way of generating. So, although we can try. We should talk more offline.
Sure, that was valuable. Thank you.
Sure. Sorry, Karen.
Okay. So, hi everybody, I'm Karen Ghavam, and I'm CEO and Engineering Director at Lunar. And so in this presentation, I'm going to be going over all the features in the SDK, not just new ones. I will be highlighting anything that's new. I did provide a QR code. I will be going over material quickly. You can follow that link and view the presentation at your leisure or at your pace. I thought I would take a moment to clarify or make it clear who is Lunar. I do get questions about this periodically. So we're not Kronos owned. We are an independent software consultancy. We are Kronos members. And we provide Vulkan ecosystem components. We've been doing it since 2015, thanks to generous sponsorship from Valve and Google that enables all the engineering work that goes behind these tools. We develop and maintain the loader, validation layers, the profiles toolset, which you'll hear more about, emulation layers that you'll find in the extension layer repository, graphics reconstruct, and more items that I haven't listed. And then we package this all up, integrated and compatible in an SDK that we deliver about every 2 months, 8 to 10 weeks apart. So I'm going to start out a little bit, just some highlights. We do surveys every year to the ecosystem users of the tools. The last one we did was in February 2023. And so a few highlights and themes that we heard from that survey. Developers are voicing needs for more development and maintenance of the shader tool chain, specifically GLSlang and DXC, DXC being the Microsoft DirectX shader compiler. It is interesting that the population of DXC users per their survey is about 20%, and 60+% of users are actually using the GLSlang workflow. GLSlang does have an HLSL front end, but only up to shader model 5. Validation layers are invaluable. I get lots of feedback about how developers could not live without the validation layers. That said, they still want us to give them more, increase the coverage of what we can actually validate while improving the performance. Error messages can really be verbose. And also, once they get error messages, it's not trivial at times for application developers to actually debug their application. What did they do wrong? There's a very strong interest in Molten VK and moving that forward more quickly. And if you're not familiar, Molten VK, Tom mentioned it, it's a Vulkan on Metal implementation. If you're interested in more detail on the survey, there is a lot more. I put a full link here. Of course, here you can't find that if you Google it, but I did give you the QR code so you could follow the link. So the Vulkan SDK, you can get it from vulkan.lunarg.com. On the upper left, you'll see a SDK link. We deliver this in close coordination with the Vulkan Working Group. Once you get to our download page, you'll see that there's versions for Windows, Linux, and Mac. And for Linux, we have 2 different versions. We have a tarball that's basically a big zip of all the repositories. Everything is pre-built. And then we also do Ubuntu packages for the Ubuntu 20 and 22 currently. We keep those up to date as Ubuntu releases come out. Downloads are healthy. As Tom mentioned, his graph must have been old because we're at 38K a week about right now for the Windows SDK. The Linux SDK, the numbers you're seeing here are only for the tarball. I don't have accurate ways to get counts of the Ubuntu packages and how many are being downloaded. But I would say that from a Linux front, we're at least at about 5,000 a week. Mac SDK is really interesting. About a year ago, there was a big jump, and it's running at about 5,000 a week now. We're speculating what caused that jump. We think it's probably related to Apple's announcements, their architecture, good performance that their architecture is providing. They did gain some market share. But then maybe it could just be because we just do such a wonderful job on the Mac SDK and people are realizing it. So we're not really sure. Okay. So why use the SDK? It's created to make things easy and convenient for developers. You don't have to. You can go try to build it all yourself. Go knock yourself out. But we knock ourselves out, making it easy for the developers. The installation process is easy and fast. The pre-built tools are installed in correct system locations ready to use. We vet the content. We make sure it's compatible so that it integrates well. There's a ready-to-use version of the Vulkan configurator. There's SDK release notes and documentation. And we also have a license registry. Some corporations are very particular about what are they pulling inside the walls of their company. This license registry will detail every single open source license that's included in that SDK. So I wanted to dedicate an entire slide to the Vulkan configurator included in the SDK. This is really a helpful and valuable tool. We do give it priority at Lunar G. We continue to enhance it. So it's a GUI application, and it really simplifies your experience with layer enablement and configuration. There are multiple preset configurations that you can use, and you can define your own custom ones as well. We recently added the capability for you to select your physical device. The next major release, this is kind of a preview. We're not exactly sure when this is going to come out, but we're going to add better controlling of the layers in terms of you could have multiple versions of a layer. Like what if you wanted 3 different versions of the validation layers to see what's going on? You'll be able to switch through those different versions and run your application. We'll provide full ordering control of the layers, including implicit layers. We're going to improve the UI with a tab-based redesign. And we'll have more diagnostics information. A lot of the diagnostics, it's driven by the Vulkan loader information. And there's a link here at Munich, Vulkanize 2023. Christoph Riccio, who is the author of this, did a tutorial there, and I've linked to the video and his presentation. So moving on, validation layers. That is, of course, the most popular tool in the SDK and the most essential. There are several different types of validation as well. There's GPU-assisted validation, validation that is occurring on the GPU at runtime. There's best practices, where you may not be violating usage of the spec, but we can detect behaviors that might not be the best way to use the API, and you'll get warning messages to that effect. And we have best practices for NVIDIA, ARM, Imagination, and AMD at this point. There's synchronization validation. Vulkan synchronization can be tricky to get correct in your application. This will validate whether or not you're using synchronization correctly. And there's a debug printf, which I just call, it's like a printf inside a shader. Helps you debug your shaders as well. Of course, the very, very simple and common layers of API dump. API dump, I think, was the first layer that we ever wrote, and it's just an ASCII output of all your API calls that you've made. Vulkan info shows you GPU device properties, etc. We also include 2 emulation layers currently, synchronization 2. You can use this emulation layer if you're running on hardware that doesn't support the synchronization 2. And just recently added as of May is an emulation layer for the shader object extension. So as you saw in the ecosystem survey, people say, give me more and make it faster. And those are somewhat a little bit in conflict if you're adding more things happening with every API call. But there is a lot of opportunity where we can performance tune. And we have a dedicated resource in LunarG who's actively profiling and tuning. Right now, our focus is on improving descriptor index validation performance. It's a CPU-side implementation today, and terrible performance and correctness problems for applications with lots of descriptor indices. So we're moving that into the GPU at runtime, and we're also refactoring it to better scale for 1 million plus descriptor arrays. This is a pretty complicated and lengthy refactor that's in progress. We're estimating it will be done sometime in Q3. I mentioned a couple performance improvements. We've done many that have been done in the past. I just chose a few that showed the magnitude of performance that we can achieve by some of the things we've done. For example, the fine-grained locking. We used to do big locks around everything, but now many, many smaller locks really helps with performance overall. So this graph is with Doom Eternal. Doom Eternal does a really good job of exasperating those areas that can get very bad in performance. But since 2021, we've been measuring the performance of it, running with validation layers, and we've had improvements up to around 150% in the performance. More to come. We're expecting a pretty big jump once we get the descriptor index performance tuning refactored to run in the GPU. So synchronization validation. So synchronization, we know, is identifying, access conflicts due to incorrect synchronization operations. And we can do it within a single buffer. We can do it within and between queue submissions and across multiple queues. The implementations are complete. There are some limitations, such as timeline semaphore. We have not yet implemented synchronization validation for that. It's very difficult and a very big project. We're currently focused instead on let's fix any community found issues so far with the synchronization validation, and let's tune it a bit performance-wise. It can also be pretty intense in performance, have some impacts on your application. So John Zuloff at LunarG is the architect and author of the synchronization validation. He's also really good at writing tutorials, and he's done several birds of a feather presentations in the past, and I added links to these, and I noticed that there are hundreds of views on these. They are really good tutorials if you're trying to understand the synchronization validation and the errors that you're getting and how you debug them. Even more tools in the SDK. So we added Vulk about a year ago, very popular Vulkan entry point meta-loader. We added Sasha's hardware capabilities viewer from gpuinfo.org. That's part of the SDK as of last October, with the option to auto-launch, so we can get more database entries into his database. The more, the better. We also support the Vulkan portability solution in the SDK. Portability enables consistent use of layered implementations of Vulkan functionality over Metal and other APIs. So there's support in the loader, the enumeration extension to give you portable conformant devices if you want them, and the portability subset extension. And we also have some profiles in the SDK for developing if you're trying to develop to the Vulkan portability solution. Okay, the Mac OS SDK. So something that's new is that we have a loader for iOS running. We don't have it packaged and delivered in an SDK yet. We're not exactly sure. There's quite a few things we have to think about when it comes to productizing this. But what this will enable now is you can run layers, such as the validation layers, natively on your iOS device with your application once we have this loader shipped to you. We also, in the next SDK, that as soon as I get back home after this show, we will work on getting released. It's going to now have all Mac SDK components support both Apple Silicon and Intel architectures, so no longer will you need the Rosetta emulation environment. And we have some good resources here. Again, we've written a white paper of how to develop Vulkan in an Apple environment. We did presentations at the Munich 2023 Vulkanize, and also we did a BOF here Richard Wright did it on, again, developing in Apple environments. He did it in conjunction with Bill Hollings of Brenwell, and this QR code will take you to that presentation and a video. We actually did a video version of this that Richard's probably editing right now and will be up very soon. Graphics Reconstruct. This tool, LunarG has invested in heavily for several years now, and it is high priority, and we continue to invest in it. There is a lot of interest from many hardware vendors in usage of this tool that have come to us asking for help to get some of the features in that they would like to have as well. So we're finding that it's very popular and quite important. It will enable you to capture Vulkan API calls in a file, in a binary format, and then you can replay them at a later time. Runs on Linux, Windows, and Android, all platforms treated with equal priority, that it works well. It's API agnostic. Today, it supports Vulkan and Direct3D 12 so far. You should take that as a hint of, yes, more APIs can come. It was architected with that purpose. Typical use cases, silicon development, we work with hardware vendors. They will use these captures to run the workflows on their simulators or do performance analysis or regression testing and bug reporting between partners. It's very common today that we will get issues on the validation layer GitHub that we cannot recreate. The user says, I can't give you my application, or I don't know how to tell you how to recreate it. We tell them, please go create a graphics reconstruct capture. They do so. Now we have a way to reproduce their issue and find out where the bug is. And Brad Grantham of LunarG, he did a SIGGRAPH BOF actually on Monday, and the QR code that you're seeing here will take you to his presentation, and he will have a video up of that presentation sometime next week. As well as he did a presentation focused more on the internals of graphics reconstruct at the Munich Vulkanize, and so I put a link to that here as well. All right, Vulkan profiles. So Tom, thank you for covering a lot of the information. It might make it easier for me to fly through some of this. But as Tom said, this will be essential for Roadmap 2024. So if you haven't been paying attention to profiles, it's time to do so. I believe we have a good tool set. So let me talk a little bit about how profiles could be used. So the roadmap profiles you've seen from Tom. So we have in the SDK today, the 2022 roadmap profile is included. And there will be a 2024 roadmap coming out at the end of the year, which will end up in the SDK as well. We have a concept we call platform profiles, and it's a way you can express Vulkan support on different platforms. So in the SDK, we have a desktop platform 2022, which is based really on Vulkan 1.1, and a 2023 was Vulkan 1.2, as well as we've worked closely with Android and put both of their Android baseline profiles in the SDK as well. Device profiles, like what if you want a profile for just a single device? So we worked with Sasha for his hardware capability viewer, and you can go choose a device, and he'll give you a profile for it in using the JSON schema in the correct format for you. There's another term we call engine profiles, where you could express the requirements of the rendering code path. This profile would help prevent an application from requiring unavailable features on devices, such that make sure they are not using features that are not supported by the rendering code path. So in the SDK, the tool set that we include starts out with, we have the profile schema, and it's just a JSON data format. It's not rocket science. It's how you communicate the Vulkan capabilities. And there needs to be a schema for each Vulkan API revision. So with every header update, we are also updating the schemas, and we're pushing up to the Kronos group, Kronos schemas repository. There's a layer called the profiles layer, and it allows you, in essence, to downgrade your developer system to the capabilities of what's defined by the profile that you give that you're opening up. There is also a header-only C++ library for profiles so that you can use it inside of your Vulkan application. It will check to make sure the device supports the profile, and then it will do a VK device instance creation for you with all the features and extensions enabled. We saved you many, many, many lines of code by doing that. And what was added about a year ago was a JSON file generation tool where you can take multiple profiles and combine them together, and you can do a union or an intersection. So this is a tool that's only been out for about a year now. There are links in this slide set. If you grab the QR code, really good tutorials on how to use the profiles tool set. Christophe Riccio has done these tutorials. He is the author of the profiles tool set at Lunar G. Okay, in the SDK, we also include the shader tool chains. So these are offline executables and API libraries for SpearV tools. If you want to validate SpearV, optimize it, the assembler, disassembler is there. If you want to go from GLSL to SpearV, you can do it with the GLSlang SpearV generator. If you want to go from HLSL to SpearV, you can use the GLSlang SpearV generator. That's up to shader model 5 plus a little bit more. And you could use the Microsoft DirectX shader compiler to go from HLS to SpearV. We include Shader C, which is basically a wrapper for GLSlang and SpearV tools for better integration into build tools. We include SpearV Cross, which will take shaders, SpearV shaders, and you can view them in HLSL Metal or GLSL. We have SpearV Reflect, which provides a C, C++ reflection API for SpearV shader bytecode. And I put a plug in here pretty quick, or at the last minute. I didn't realize this happened. This happened several years ago. Spencer Frick, who's at Lunar G, created a really handy tool to visualize your SpearV and donated it to Kronos, and this is a link where you can find that visualizer. It's a very useful tool, and I'm going to make sure it's included in the SDK documentation as well. So again, the link to today's presentation, if you realize that I went faster than what you could keep up with, or if you want to get some of those links. And there will be a networking session after this Vulkan session. We will have a demo table there. Brad Grantham, who's the technical lead for Graphics Reconstruct at Lunar G, he will be demonstrating Graphics Reconstruct for you and showing how you can expect an application's graphics commands using it. And then Richard Wright, our Mac OS enthusiast inside Lunar G, he'll show you Vulkan validation on Apple devices, and he'll also demonstrate Vulkan Configurator for you. And with that, I think I'm all done.
So, hello everyone. In this section, my colleague Bernhard and I will talk about, not about the future of Vulkan, but about the future users of Vulkan. Teaching Vulkan is a delicate process, and mastering Vulkan requires a blend of theoretical understanding as well as a lot of hands-on experience. And we will show you how we do this in an academic context, but we also had a Vulkan course at this year's Vulkanized. So at our university, we teach 4 different computer graphic lectures. We have 2 undergraduate lectures and 2 graduate lectures. The order of the images is the same order as the courses are listed here, while the first or the courses shown in the middle here let the student decide the graphics API that he wants to use by himself. The first and the last one here constrain this to in the beginning OpenGL, but now we also have this in Vulkan. So in this talk, I will mostly talk about this, or only talk about these 2 courses, one from an undergraduate perspective and one from a graduate perspective. it's important to differentiate this because you have to use different methods to teach this to a different audience for Vulkan. So how did we transition to Vulkan? We had multiple options to do this. We could have just created another new course, but here the question is, should we enforce this to every student, or should this be an optional course? And also this would maybe change the curriculum also that we teach. Or we do Vulkan teaching only in a graduate course. So the undergraduates will still use maybe OpenGL, and in the graduate courses we would switch to Vulkan or change everything to Vulkan straight away from the beginning. We kind of went with the last approach, but we choose to slowly integrate Vulkan into our teaching. So this is minimal, this is least invasive curriculum-wise and also beneficial for students. Maybe not every student wants to go the Vulkan route. But at the same time, with a lot of work, maybe we can bring this to a status where even for people that just want to taste a bit of computer graphics can also use the Vulkan route. So for the undergraduate course called Introduction to Computer Graphics, we decided to do a dual track mode where students can decide if they want to do OpenGL or Vulkan, and this exists since 2021. For the graduate course, which is called Algorithms for Real-Time Rendering, we started out with a 50-50 tactic, where some of the tasks were in OpenGL and others were in Vulkan. Mainly, for instance, the ray tracing parts of this course were done with Vulkan. And since 2022, this is only Vulkan, so the graduate course is completely shifted to Vulkan. So there are different requirements needed for a different audience, and we differentiate here with beginners and advanced. Often beginners have never seen a graphics API before and just start out with our course, and they require concrete guidance, while advanced users want to explore this a bit on their own, and we can provide them just a vague guidance. Of course, for beginners, it should not be too overwhelming, and Vulkan can be overwhelming if you throw everything at them at once. And at the same time, for advanced students, you don't want to make it too boring. And an important aspect when teaching Vulkan is the abstraction. For beginners, it's important to start out with a high abstraction and then remove parts by parts, like an onion, for instance, and remove more of the underlying ways how Vulkan functions. And for beginners, it's important to also get the concepts and the patterns and how everything is a bit connected without giving them too much low details. And for advanced users, it's important to give them useful, or at least in an academic course, it's important to give them useful abstractions so they don't waste too much time on implementing everything themselves. And the insights, of course, for an advanced student is to get low-level details on the one hand for Vulkan, but at the same time, we also want to implement state-of-the-art graphics algorithms. And we developed two different frameworks for this case. For the beginners, we have Vulkan Launchpad, which we also applied during the Vulkanized course, which is basically a very high-level abstraction layer. And AutoVK is more at the level of, for instance, Vulkan HPP, like the C++ headers. And yeah, so let's start out with the introductory course here. This is often the first contact with a graphics API. It's maybe not the first contact in our university with rasterization because we have some computer vision courses before, but until this point, they mostly never have used a graphics API. We have about 150 students per year, and the task, we have basically 5 assignments. And you can see the images here from left to right. It's assignment 1 till 5. They learn how to draw some simple shapes, translate them, move them around, create different pipelines. As you can see here, that do back-face culling or front-face culling and so on, and all these variations. And they do basic shading. And the final assignment is then do some texturing. The thing is, the original OpenGL assignments were around 1,200 lines of code. And as some of you know, drawing a triangle in Vulkan is already 700 lines of code. So we needed to add some help or some abstractions to that so that we can keep this in check. And maybe this is even a good thing that we have this comparison between our OpenGL course and the Vulkan implementation, because it allows us to keep track of the required work. So let's take a closer look at task 1. In this task, the goal is to open a window and do some basic setup, basic Vulkan setup. So they need to choose the device and activate, like I display here, need to initialize the instance, create a device, pick a physical device, create a logical device for that with extensions enabled, and pick a queue, and then call the framework, and then basically the framework takes over. The framework does the rest. So this is a code snippet. So everything above the VKL init framework is done by the student using the C API of Vulkan. They create all these handles, and then they pass this to this function. And also the while loop below is also written by the students. They can use GLFV is used for creating the window and doing the input handling. And then they use these predefined functions that are often in the task description or so, and create this render loop. And the good thing is students can already see the result and get a dopamine release. And I think that's a good way of giving them a first impression of Vulkan. And then you can always like strip down things and go into more detail for these sections. For instance, we can replace the init framework part or the loop itself, or we can just replace the VKL draw T part here and replace it with the actual command calls that they need to do. And through this way, we can keep the implementation overhead in check, and students can still understand the fundamental components and how they are connected. So a bit of statistics here. This is from 2021 and 2022. The number of Vulkan users increased in 2022 and 2023. Here we have about 15% of all students using, like 15% of all registered students chose the Vulkan route. Now it's around 25%, even though we told them that the Vulkan route or Vulkan path will probably be a bit more effort. At the same time, the grades for the Vulkan students was better. So maybe that's because we got only motivated students for the path, for the Vulkan path. Yeah, maybe that's the reason. So at the same time, Vulkan students finished all the tasks faster than the OpenGL peers. Maybe we created a too good abstraction for this, but based on the survey, they were quite happy with what they learned. Now let's go to the advanced lecture that we offer. Here the topics are quite broad, like we teach state-of-the-art algorithms for real-time rendering, like hardware deceleration, view frustum culling, physical-based shading, temporal anti-aliasing, and also real-time ray tracing. We also provide some framework that does the scene loading, window input handling, and also abstract some parts of Vulkan a bit so that it's more easier for the students to go along. So we try to provide convenience function without hiding functionality, And I just give a small example here because I don't think that we need more of these examples. So here you can create a pipeline just by using this variadic function, and you insert the shader path or where your shaders are located, and you can specify the winding order and the vertex inputs, and specify some bindings. So here another statistics about the number of students over the years. The algorithms for real-time rendering is only offered every 2 years, so that's why it's missing in some of these plots. As you can see, maybe I need to clear this. The real-time rendering is the project-based lecture where students need to develop a game and choose their API independently. So even before we started doing Vulkan at our university, there were already some students trying Vulkan during these courses. And then 2021, we started to offer this Vulkan path. And as you can see, 1 year later, we doubled the number of Vulkan students. And the same with the computer graphics exercises is the same like the real-time rendering exercise is also like a project-based lecture where students can choose their API independently, and they also started to using Vulkan there. And yeah. So I just want to throw this question out there. So what is the future path that we should take when teaching Vulkan? I don't really want to get into this rabbit hole, and I'm not even sure if it's already time to ask this, but we kind of going in a classic and modern Vulkan direction split. For instance, render parsers and frame parsers are mostly replaced by dynamic rendering. Pipelines now kind of get in this direction of shader objects. Descriptor sets are often used as with the descriptor buffer extensions, or why use buffer attachments at all and maybe just use buffer references for bindless rendering. Maybe the interface part is a bit far-fetched because that's a personal preference, and you can always use the C header for modern features. But for me, at least, it's not really clear what we should really teach going forward. In our introductory course, we just use Vulkan 1.0 and the C headers, but maybe some of these parts could be replaced with more modern features. So, and that already concludes my part. I want to talk about a few. Want to summarize the resources that I used. Maybe some of you know the awesome lecture series that Johannes Untergutenberger did, which you can find on YouTube. On the right, you can see some of our tools that we use. For instance, the Vulkan Launchpad. If you're an educator, then maybe you can make good use of that and create your own tasks for whatever audience you want. And all of this is basically based on an educational paper by Johannes Untergutenberger, Bernhard, Kerbl, and Michael Wimmer. And speaking of Bernhard Kerbl, he will be the next presenter now.
So, okay. Thank you for your patience. Here we go. Okay, Lukas, thank you for your very first nice first part. So, Lukas was talking about maybe taking some different approaches and deciding between modern, classic Vulkan. And this is, again, something that we tried here with a different approach with Vulkan for compute. Again, this was kind of a know your audience challenge. And I'm gonna describe what we did differently here for a different type of audience. So, first of all, why would you want to look into compute? First of all, it's definitely on the educational side, because if you do compute, you have to analyze all these different capabilities that you have. You need to be aware of if you want to do efficient compute. You need to know what kind of hardware resources your classical GPU has, how you can exploit them, so you can really take the time to drill down into the individual components and make sense of the individual parts of your hardware. And of course, once you understand them, you can use your GPU not only as something that makes pretty images, but basically as a general purpose side processor that helps your CPU with nice parallelizable tasks. And once you have enabled and unlock these features basically both in your mind and the API, you can then start from this and really focus on the performance aspect. And compute basically gives you a few simplifications in Vulkan. It's faster to set up, it's somewhat less verbose, which we will see in a second, and you can make it even less verbose if you do a few tricks. And so with these things in mind, hopefully what's coming up now is a healthy mix of suggestions and tools and experiences and maybe some motivation to start teaching Vulkan or integrating Vulkan as a way to teach compute. So another reason that is not on this slide here, but is definitely important, is that compute is not only valuable for doing things like number crunching or computing your machine learning outputs, but it's becoming more and more important in graphics applications as well. So we see more and more applications that make very heavy use of compute, whether it is for simulation, whether it is for neural rendering, or whether it is for actual classical rasterization, but with a twist, so-called software rasterization, which also more and more attracts attention from compute. So the first part of why one would argue that compute is easier to teach or might be a nicer way to make Vulkan approachable for students is that if you compare the stages of the graphics pipeline and the compute pipeline, it's actually pretty obvious. So you only have that one stage that you need to care about, right? So that's a very nice visualization of how this could be differentiated in terms of complexity between the two paths. But we will see a little bit more about this. So what they basically do is targeting a specific audience, which in this case, or for this type of course, is not strictly university level, but also includes an audience that is a University of Applied Science level. They basically get a set of 13 tasks, where the first 12 are explicitly guided, and they are kind of laid out in a way that is more like a puzzle structure. So this is somewhat inspired by, I don't know if you're aware of these challenges, like for instance, Advent of Code. And you can basically translate these kind of setups also into Vulkan, right? Where if you do your synchronization correct and you do your buffer copies correct and maybe you wrote your shader correct, you get a nice little message at the end of the day, and otherwise you get some gobbledygook that makes no sense, right? And these assignments basically try to go that way and progressively up the ante until you get something that is really interesting and also visually pleasing. Because you can make things that are visually pleasing without ever setting up a graphics pipeline. It's super easy to compute something that is interesting visually, then write it out maybe to an image, and then you have, again, that dopamine release, but with even fewer lines of code. So, where can you find these exercises if you're interested in them? They have been now alpha tested by the HPG audience this year. So they are available under this link. Unfortunately, I also don't have a QR code, but I hope that this one is somewhat easy to remember. Consisting of these 12 hands-on programming exercises. So this is now in beta. If you want to do something to it, if you want to make suggestions, please feel free to reach out. And also if you have ideas for introducing new sub-projects, maybe ease the learning curve a little bit more, that would be great. So for teaching compute, what is the rationale here, what we tried to do? So we took a path here where we said we don't want to do any abstractions, and that's feasible because compute is much less verbose. So we don't have any support for the students in terms of framework. They get to write real code from the get-go that you would use in the industry as well. But we use the available tools that are there that make things more convenient, right? So there's no framework structure there, but we basically nudge them towards using tools that are meaningful. And this aligns also with the demands of the different audiences we have. Again, so this would be, for instance, the setup for making a simple device. And this is the C-style API of Vulkan. Especially for us, we said we want to be modular, we want to reach a broad audience, university or University of Applied Sciences. Especially for the latter audience, you don't want to try and teach them a C API. They will not take kindly to this, especially if C is not in their applied curriculum. So the first switch or the first takeaway for making things easier would be to don't try to teach C API. And here you have basically Vulkan HPP that comes to the rescue. So you have those C++ style extensions, including constructors, RAII wrappers, and very clear and unambiguous namespaces that help shorten your code and reduce the risk of errors. So the same code that we saw before for setting up your first device with Vulkan HPP, if you've never seen it in action, is much more compact and is much friendlier to a student, especially if they are used to using those standard containers of the standard library, and Vulkan HPP allows them to integrate them with things they might be much more used to. So only using Vulkan HPP, let's see what we need to do in order to get your first Vulkan compute equivalent of Hello World, right? You know all the steps already. You have to go through all of these that are listed here. You have to provide your GLSL or whatever other shader code that compiles to SPIR-V. You have to make your instance, your device, set up a compute pipeline, then record a command buffer, and then make a submission, and in the end, finally synchronize. So what does this look like? Well, how fast can you do it if you use Vulkan HPP? Well, you can do this in basically the equivalent of a check card. So here, basically, this includes the entire code that would be needed to write your first Hello World program in compute. And you have very clear distinguishing setup of what you need to do here. Here's the basic Vulkan setup, including the instance and the device and the queue. That's all in there without any frameworks. That's just Vulkan HPP doing its job. You have even the shader code in here for good measure. So that is the shader code, shader module, compiling the shader code, then combining it with a pipeline. And then lastly, you have the setup of your command pool, the recording, and lastly also the dispatch. And then in the very end, you have the wooden mallet of synchronization that is a device wait idle, right? So, and if you run all of this, what you get is the equivalent of a Hello World, but parallel, right? So already you have unlocked the power of your GPU. You have not printed Hello World once, but 8 times, so great. This is maybe not entirely user safe on its own. So you would, of course, have to, if you're doing this properly, make sure you have your extensions, you have validation layers enabled. So how can we make it so that this becomes actually proper? That is in making sure that we have our validation layers and our extensions enabled with the help of another tool. That is my second takeaway, and that is be brave and make sure that you can appreciate VK-config and that the students can appreciate the ease of use and the usefulness of VK-config, as we've heard before. So you can set up your individual environments with the VK-config with just a few clicks, and it can completely replace your validation layer setup. And at Vulkanized 2023, I had a nice talk with its creator who basically said, yes, that was the wider vision, or that was the greater vision for this project. And a nice little addition is that also the VK-config creator allows you to very easily enable or disable the printf functionality without ever touching your code. So another example that I want to look into, or another step for making things more compact and making it easier for students to grasp is, this is one of the tasks that you need to do as part of the exercises that I have in this suite. And that's like a decently sized wall of code. And all you're pretty much doing here is setting up your uniform buffer, right? So Vulkan HPP on its own will not help you there. What will help you there is something that also comes with the SDK, and that is the Vulkan memory allocator. So unfortunately, at this juncture, Vulkan memory allocator pretty much, as it is being maintained, only has a C-style API. There are some C++ versions out there, but I'll come back to this later. Another part at some point during the teaching of the Vulkan Compute API to students, you will need to convey to them what it means to exploit the collaboration within the GPU, because that is the main reason of why you would want to have them switch to compute so they can make computations efficiently. And making GPU compute efficient means to exploit the collaboration that you have between the different layers of the execution hierarchy, right? So, for instance, in the very simple case of a reduction, where you have your arrays of values and want to compute a sum value, a simple way to exploit the collaboration techniques that you have available on the GPU is to use the shared memory that you have on each individual compute unit inside your device. And of course, a very simple way to do this would be to first tell your students what is an atomic operation, then tell them that there's something like shared memory, and then let them try an experiment and how they could give them a basic idea how they could basically combine values first into shared memory and then into global and get some savings. And they might come up with something like this. So in theory, this should be a more efficient solution to the problem of the reduction of values to a single value. But unfortunately, as many of you can tell from looking and without thinking too much, this is wrong, right? And so this first example that many students come up with, or this first solution that many students come up with, basically brings you to the necessity of making sure that you need to tell them properly about multi-threading and memory. And this is an issue because it doesn't really come up that often, or there is hardly ever a curriculum that looks at this in depth and basically really drills down into a C++11 style memory model and what it implies, right? So the memory consistency is key whenever you exchange information between threads. And in theory, students know this, but the experience that they have is usually in most cases on a multi-threaded x86 architecture, which by default will be using sequentially consistent operations. So that is mostly what they are familiar with. And on the GPU, the default operations that you have for atomics would be relaxed, which is the nightmare of anybody who is coming from the CPU and doing multi-threaded programming, and this is basically the default behavior. So if you're approaching this, at some point you will have to give them a basic overview, a basic introduction on synchronization, because probably nobody else has done it before to the degree that they will need to have it. So basically making sure that they are aware of what memory fences are, how does release and acquire semantics make sense, things like out of thin air values, luckily you can skip them because the Vulkan memory model doesn't allow them, so that's already great. And what's also important to remember is that synchronization, at first might look tough, but it really isn't if you have performance to spare. So if it makes sense to maybe not prioritize performance early on when you're teaching students, you might use those very slow, very expensive synchronization primitives, and then later at some point come to the less expensive ones and introduce them gradually. And another thing that I would like to maybe incentivize or maybe give the idea is to maybe pursue synchronization as a challenge of gamification, because I think it can be put into the form of individual puzzles where you start out with a code that does something, follows some instructions, computes some results, combines them together, copies them together, and at the end you get a value that at first is wrong, but as you keep adding more and more synchronization primitives, you basically end up eventually with the correct result. And this could hopefully also be supported by something like the validation layers for synchronization or the emulation layers, as we've seen just before. But I have no clear way, or I have no clear roadmap for making this, although to me, honestly, this sounds like it would be quite fun. What are some open challenges that we have? So as I just mentioned, Vulkan has a complete C++11-like memory consistently model, both for shared and global memory. But right now, there's currently no standardized forward progress guarantees. So what does that mean? That means that many of the algorithms that you would want to do with a C++11-like memory consistency model, right now you can't do them because in addition to that, you would also need forward progress guarantee, which is not yet there, but is in the future actually of the specification, which I was basically told in some internal chats or some private chats at the last Vulkanize conference. So it is very likely that actually, as some future part of the specification, we will also have forward progress guarantee. So that's great. It supports a wide range of cutting-edge and vendor-specific features, but for instance, some of the popular ones that you might know, for instance from CUDA, they are not there yet or might probably never make it in there. So, but this is again, as we heard before, this is often influenced by the demand and by vendor policies. So we will see as demand rises, maybe at some point we will have also for these somewhat interesting extensions, we will have additional functionality inside Vulkan. Third point, I already mentioned this before, it would be very nice to have a solution for the Vulkan memory allocator that is compatible with Vulkan HPP, so that you don't have to break these coding paradigms and can keep the RAII behavior. There are unofficial GitHub projects that are trying to do this, but those are unofficial, and the support for future versions and for future functionality is kind of vague, so I personally don't recommend at this point integrating this into a teaching experience. And the last point is that basically with Vulkan, there's a very steep challenge of keeping up with the nice SDK environments of other compute APIs, which give you a very extensive set of features. And we know that Vulkan can do the same jobs with the same performance or even better. We saw this, for instance, at the last Vulkanize conference, where we saw the presentation of VKFFT, which, by the reports of the author, breaks even and can do basically similar, it has a similar efficiency as the CU FFT libraries on the same hardware, and in some cases can even surpass it. But of course, other APIs have these functionalities and have maybe a more extensive set of these functionalities and libraries. So this is really something that is a question of, can the community find time to add that support also to Vulkan and make contributions also to Vulkan in this kind of, in this form. And yeah, this brings me to the conclusion of my teaching experience for compute. Thank you so much for listening to me. Thank you also to the contributors to this course, anybody who's been involved in this, at TU Graz, TU Wien, and FH Salzburg. Of course, thanks to SIGGRAPH and to the organizers who did a lovely job bringing us all together here and establishing a nice network for communications. So thank you.
All right, yeah, I think we're set up. Yeah, so we'll all run off the same laptop here, so I think we're good to go. So we have 4 speakers from Autodesk. My name is Henrik, so I'll go first. Before we start, I got to show this slide. We will be making some forward-looking statements. Plans might change, so please don't make any purchasing decisions based on what we share here today. So I'm going to start with kind of like a high-level overview where Vulkan fits into our pipeline and yeah, what type of use cases we're trying to solve here. And then I have 3 colleagues here that will go more into the details in how we specifically use Vulkan for different parts of our graphics stack and products. So you probably are somewhat familiar with Autodesk, but we make software for people who design and make things. And that's for AEC, architecture, engineering, and construction. It's for product design and manufacturing, and it's for media and entertainment. And obviously here at SIGGRAPH, we tend to highlight a lot of the work we're doing in media and entertainment. But AEC and product design and manufacturing are our biggest industries where we have most of our products and most of our customers. And obviously all these industries have need for high performance cross-platform graphics. So across these products, we have a need for a wide range of capabilities, ranging from 2D drawings, more simple types of 3D scenes, typical kind of 3D modeling workflows where you might have some simple shading just to be able to read surfaces and so on, but you typically don't have any texturing or advanced lighting or things like that, and might actually be in the way for your particular workflow. And then we also need to support realistic rendering where you want realistic materials, lights, shadows, reflection, glow illumination, and so on. So most of our products need to support all these different styles of graphics. So it's a pretty broad range that we need to cover with our graphics stack. So I'm specifically talking about our viewport graphics here. There's other workflows around graphics as well. But most of our main products are on a common graphics stack. Flame, that Jasmin is going to talk about later, is one exception. It uses a separate stack. But most of our major products are on the same graphics stack. And that's currently undergoing major modernization, I would say. So the objectives here is to make sure that we fully leverage the current generation of APIs, including, of course, Vulkan, that we are using open standards and open source as much as possible. These are just a few examples, USD and Hydra specifically, MaterialX, OpenPBR, OpenColor.io, and others. And we also have an intent to decouple our applications from the graphics stack as much as possible. Because if there's one thing we know about graphics, is that it's evolving quickly. We have new hardware capabilities, new APIs, new algorithms and techniques, and we want to be able to quickly adopt those and integrate them into our products with minimal effort. And all of this needs to be available on desktop, mobile, and web. So for desktop, that is Windows, Linux, Mac, mobile, Android, iOS, iPadOS, and web, obviously all the major browsers. So if we look at all these things, modern APIs based on open standards, decoupled architecture across all the various different platforms, that led us to the decision to base our viewport strategy around Hydra. So Hydra is this open source library. If you were here for the INRIA talk earlier, it's kind of the same principle. We just started working on Hydra before the INRIA project started, but the principle is the same. So it's a way to decouple how the applications describe the scene data to the graphic system from the implementation of the graphic system itself. So on the front end, we have something called a scene index, which is the way that an application, whether it's a desktop, mobile, web application, describes the scene data to Hydra. So that kind of represents the multiple different heads of a Hydra. And on the other side, you have something called a render delegate, which there are several different render delegates, many external, non-Autodesk, but there are three main ones that we are looking at internally. So the first one is Storm, which is the rasterizer that comes with a USD distribution. And that's kind of handling most of the type of graphics that I described earlier. Basically, for our viewport needs, it's probably about 99%. It's all the 2D, all the 3D, all the modeling workflows, and so on. When it comes to realistic rendering, where you typically want to have something that is ray tracing based or path tracing based, we have Aurora, which Mauricio is going to cover in a minute, which is a real-time path tracer, kind of a game-like experience, but with full global illumination, reflections, and all of that. And then we also have the Arnold renderer, which is our production renderer. So that's specifically used for like high-end VFX film type of workflows, which is a bit different. It's also not using Vulkan, so we will not talk more about that today. But both Storm and Hydra use another abstraction layer within the Hydra stack, which is called HGI, Hydra Graphics Interface. And that is the low-level API that abstracts the underlying APIs like Vulkan, Metal, DX12, and WebGPU. So what we will cover here today is Storm and Aurora and how they both use Vulkan through HGI. And again, this is something that we are incrementally rolling out for several of our main products, not including Flame though, so keep that in mind when we go into Jasmin's talk. But this was just to kind of frame the next two speakers' talks to understand where Vulkan and Storm and Aurora fit into our stack. So with that, I'll hand over to Mauricio.
Thank you, Henrik. Okay, so as Henrik mentioned, I'm Mauricio from Autodesk. 5 years ago, quick story, I was at the WebGL BOF to talk about 3D retail space planning, and such is the technical diversity of the Kronos group that I'm here to talk about something quite different. So, and that is Vulkan ray tracing in Aurora, which is our open source real-time path tracer. Now, much of the work I'm showing here was done by my co-conspirator Gareth, who could not be here today. So, once again, we have a safe harbor statement, so please don't bet your life savings on what I'm about to say here. Okay, so my part is going to be a series of questions, starting with what is Aurora, in case you don't know. The first thing I want to mention is that Aurora is open source and free as in beer. In fact, everything that Henrik talked, I don't know if you said it, but everything that Henrik talked about in that last slide, all the stuff that we're doing is all going out into the open, right? And it's open source, including Aurora. So besides that important thing, which we'll get to again later, it's also these things. I will touch on most of these in the next few minutes, so I'm not going to, you can use your eyeballs and read them. The last point in italics there is important. We developed Aurora for rapid design iteration, not final frame rendering. So it's more for powering an application viewport and less for rendering a movie. If you want the final frames, that's what we have Arnold for. Please go check that out. Anyway, so let me show you, or attempt to show you, Aurora in action. So this is Aurora running in our demo app with this telescope model that we made available for the open source release. So we released it in open source in November, I think it was November, and we released this model with it as well. So if you want, go take it, use it in OBJ or USD format. So the demo app sets a frame performance target, in this case to render as many samples per pixel as possible in like 33 milliseconds, and then we apply denoising. So a lower-end GPU still runs smoothly, but may have like more temporal artifacts or noise until you let it sit idle. So here I'm animating the background. I think I stopped it there. But yeah, the environment light was animated, which shows that the shading is fully dynamic. Nothing is baked. So, path tracing. All the benefits of path tracing are here. And again, as you're watching this, the goal is rapid design iteration, not final frames. A product designer in the middle of dragging a slider for a material property is more interested in responsiveness than a perfect final result. Hopefully that makes sense. We think we've struck a good balance here. So, next question. Where is Aurora used? So, Aurora is already shipping an Autodesk Inventor as the new GPU ray tracing feature. So this, on the right side there, is a screenshot of a 3D printer model in the Inventor viewport. We're also exploring the use of Aurora in other products, but I can't speak on behalf of those product teams here. Of course, since it is open source, anyone else can use it too. So all we ask is that you let us know if you do use it, because we're curious to hear about it. Before I move on, I want to show what Aurora looks like inside the Inventor UI. And so basically all you have to do is click that little ray tracing button up there to get going. You load your model, you sort of switch to this sort of realistic mode, click ray tracing, and off it goes. So that's how it works in Inventor. It's designed for engineers, not artists, so simple is good. Okay. So that list on the first slide mentioned that Aurora uses hardware ray tracing. So in case you don't know what that means, and I don't think we've covered it yet in this BOF, let's answer that question. So what is hardware ray tracing? So basically it's graphics API support for ray tracing operations. What's kind of funny is that it may or may not be backed by actual dedicated hardware. So some older GPUs support hardware ray tracing without actually having the dedicated hardware, but that's because it's hidden behind, compute shaders or something. Obviously, that will be slower. Dedicated hardware is a good thing if you can get it. So it was introduced with DirectX ray tracing, or DXR, at GDC 2018. And the hardware, that dedicated hardware, I should say, from NVIDIA followed shortly after in the Turing architecture, or basically once they started calling everything RTX, that's what they were referring to. They're referring to this ray tracing hardware. So this is how Jensen of NVIDIA introduced this I think it was in Vancouver at SIGGRAPH 2018. He sort of held up a GPU and had it reflect the light and say, oh, look, ray tracing in real time, right? So it was super corny, and I loved it. So this is now widely supported. It's not just NVIDIA, but NVIDIA, AMD, and Intel all have support for hardware ray tracing through these APIs. Even in integrated GPUs, and I really want to spend just a moment on this one, starting with this AMD Radeon 680M. So this here is a die shot of a Ryzen 6000 series processor, which has an 8-core CPU, which if you look closely, you can see the 8 cores sitting there, and a GPU that supports hardware ray tracing right there on the die, right, the little tiny little die. So this little laptop, the one I'm using right now, supports hardware ray tracing. So my point is, it's here to stay. It's not some kind of flash-in-the-pan feature that's going to get yanked by the vendors. Oh, nobody's using this, so this is going to go away. We are stuck with it, or rather, we are the beneficiaries of hardware ray tracing now and forever, as far as I'm concerned. So just keep that in mind. So when you do have dedicated hardware, it normally handles two things, BVH traversal and triangle intersection. And then the API introduces a few new things. They are acceleration structures, ray tracing shaders, special shaders like ray generation shaders or closest hit shaders, shader binding tables, and special commands to sort of invoke all of this stuff. So you'll notice this is the Vulkan BOF, and I haven't said anything about Vulkan yet. So let's fix that right now. What about Vulkan? So Aurora development started with DXR support for Inventor on Windows, right? So we only needed it for Windows at the time, or at least that was the thinking. But as we got to this open source release, we thought, well, we want Linux support for other Autodesk products that happen to run on Linux as well. So we want cross-platform. Vulkan is the answer. So Vulkan it is. Ray tracing support in Vulkan was finalized in, I think I got this right, December 2020, which is great. And it's conceptually very similar to DirectX ray tracing, so once you know one, you kind of know the other. But it's also just as verbose. Earlier we heard, some like 700 lines to draw a triangle or something. With Vulkan, Vulkan ray tracing is also verbose, just like DirectX ray tracing. So, APIs, toolkits to sort of abstract that are great and much appreciated. So this is a blog post that I highly recommend if you want to know more about Vulkan ray tracing, and it includes this. I am not going to go through this, don't worry. Really nice diagram from the blog post, which is clearly more than I can do here. However, you are in luck. The last presentation in this BOF will be about debugging Vulkan ray tracing, so that'll be in about 30 minutes. So we are going to hear more about Vulkan ray tracing. You may ask yourself, how does Aurora support Vulkan ray tracing? So we are using... There's the key bit. We're using HDI instead of a direct integration. And the reason for this is it makes it easier for the Hydra render delegate that we have. So Aurora includes a Hydra render delegate. So Henrik just briefly mentioned what the HDI is. Let me just make sure you got this. OpenUSD includes something called Hydra. Allows you to mix and match scene data and renderers. Mix and match scene data and renderers. Hydra includes HDI, Hydra Graphics Interface. It is lowercase gi. I don't know why. So HDI is an abstraction layer over graphics backends. So OpenGL, Metal, and Vulkan. It's intended for, again, for use by Hydra render delegates. That's the real idea there. But it can be used independently, and that's kind of what we're doing. Now, I will say the HDI Vulkan support, in case you've been following it, is incomplete. It doesn't do everything yet. It's not really usable for now. But see the next talk right after me. We're going to talk a little bit more about that. So this is not the last you've heard from HDI. Now, for our purposes, for Aurora, we didn't actually need all of Vulkan. We just need enough for ray tracing, right? So what we decided to do was extend the HDI API and the Vulkan backend as it exists today to support ray tracing. So that means adding, this may seem familiar, acceleration structures, ray tracing shaders, shader binding tables, special commands. Okay, so that's what we added. Let me dig in a little bit in that. So what did we actually put in there? So these are some of the types and enumerators that we added to HDI to support ray tracing. Okay, these, if you're familiar with Vulkan ray tracing, these closely correspond to concepts in Vulkan ray tracing, then if you look at those names. So it ends up being a fairly thin wrapper, at least right now. Like Aurora, this extension is also open source, and you can find the code in this branch of our USD, Autodesk USD fork. So it's not in the OpenUSD official yet. It's relatively new. Hopefully it'll eventually get there, but that's where you can find both the additions to the HDI API and the implementation of that API in the Vulkan backend. It's sort of two things in one. One of the main challenges that you have to deal with when you address multiple graphics APIs is this one. What about shader languages? Bane of our existence. So we needed both HLSL for DXR and GLSL for Vulkan. We don't want to maintain two copies. I've been there, I've done that. It's no fun, although you could do that, I guess. And we don't want, so what we need is shader language translation, right? We'd like the computer to do the job for us. Isn't that nice? And we heard a little bit about all the different ways that you can, all the tooling for shader language translation. But here's the catch. We need support for ray tracing concepts like, you know, there's a trace ray function, right? And a lot of those tools haven't caught up to Vulkan ray tracing. So what to do? Slang to the rescue. So Slang is an API or a toolkit from NVIDIA. It originally started, I think, at Carnegie Mellon and as a paper, and you can go learn all about it. But their tagline, the important thing is their tagline is making it easier to work with shaders, and that's what we found. The code then in Aurora is written in Slang, which is basically HLSL with some extensions. That's basically what Slang is today. And then at runtime, the Slang transpiler will convert from GLSL, convert to GLSL, I should say, when the Vulkan backend is used. So this was basically, in my opinion, a seamless integration, except for a few minor if-defs. So you go look at the code, you'll see a few if-defs, but that we may address later. But overall, it's basically the same code for both targets, right? We aren't using the advanced language features that Slang has, but they are compelling. If you do want to know more about Slang, you should check out Falcor from NVIDIA, where this is where a lot of their path tracing research code goes, and it uses Slang extensively. So I highly recommend you check that out if you want to know more about Slang. So now I want to show you how all these pieces fit together, sort of to begin to wrap up. So we have a typical rendering API upon which we built the Hydra render delegate, which is called HD Aurora. That's the convention. And then we have the demo app that I showed you earlier, the video, is called Plasma. So we have the two implementations I mentioned, which are DirectX and HGI. And when the HGI implementation, you sort of choose one or the other at a time, right? When you choose the HGI implementation, especially if you're running on Linux, you have to, we use the HGI API, which that dashed line there, and the Vulkan backend, which has our ray tracing extension. So in the future, there might be other HGI backends that support ray tracing using that same interface. So the idea is that we want to stabilize on the interface. We may make some changes to it or whatever, and then there could be future backends. You can think of some probably off the top of your head, like DXR. We could actually just bring that DirectX implementation in there, for example. But anyway, that's for the future. Speaking of the future, what are the next steps for us? First of all, we need to address some known gaps between DXR and Vulkan and Linux and Windows. It's mostly around like windowing and interop. So we need to, one thing that we need to do, and it's kind of an interesting thing, we need to refactor our integrator to be iterative instead of recursive. So our path tracing integrator is actually recursive. But it needs to be iterative. Why? So it's a good thing that should help performance, but it also addresses an interesting limitation with some Vulkan drivers where they don't support multi-level recursion, right? Since it's not mandated by the spec. What's interesting is the same vendor supports recursion on DXR, but not on Vulkan. I don't know why. If anybody knows why, come talk to me. I'm kind of curious. But in any case, it's something we want to do anyway. We want to have it be iterative instead of recursive. And so that'll give us broader compatibility. That'll be Vulkan support on more GPUs. So that video I showed has denoising. We don't have that in the public repo yet because it's an old version and we need to update to the latest that NVIDIA provides. It's called NRD, real-time denoisers, NVIDIA real-time denoisers. The good news is Vulkan is supported by NRD, so if you want to use it in your project, go ahead. It's good for us because we're going to use that Vulkan support when we turn that back on in the public repo. So upscaling with AMD FSR is another thing that we have in mind, and Vulkan is supported there too. How convenient. And Material X support for Vulkan is not working yet. So if you have the DXR version, you can sort of use Material X materials, and it'll run it through Material X, and you get the expected result. But not yet on Vulkan, so that's something you have to fix. And then while we're in there mucking about with Material X, maybe we'll integrate OpenPBR, which is you should go look it up. It is sort of a successor to Autodesk Standard Surface and the Adobe, I think it's called Standard Material. Okay, yeah. So those things are being merged and made open, so go look it up. It's actually very cool. That was just recently announced. So we may, we probably will put that in Aurora, I guess. So yeah. let's see here. Last but not least, as I mentioned at the very beginning, Aurora is open source. So if you want to help with any of these things, or there's something you're interested in that you don't see on this list, you can contribute. The repository link is right there, along with an email address if you want to contact us directly. So that's all from me. Now I'm going to turn it over to Vipul, who's going to tell you more about how we are having fun with Vulkan at Autodesk. Thank you.
Hi everybody, I'm Vipul Kapoor and I work as a graphics engineer for the platform team at Autodesk. I'll be talking about how we're using Vulkan as a cross-platform strategy for viewing large AEC models. That is our safe harbor statement. In this session, I'll talk about what AEC models are and how they define our technical problem statement. Also, I'll talk about what our cross-platform strategy is and how it aims to meet our rendering challenges and demands at Autodesk. After that, I'll talk about where we currently are in our process of using Vulkan on this journey and a little on how we got here. And finally, on community and collaboration. AEC stands for Architecture, Engineering, and Construction. And so the design data, so AEC models are design data for building infrastructure and construction projects. This data format is optimized for design, and it's sharing between different engineering teams and different perspectives. So this is unlike game development models where it is authored by taking some rendering optimization strategies into perspective, like LODs and vertex overdraw and stuff like that. For some perspective, they include both 3D and 2D information. The 3D information is the three-dimensional representation of what the design data is itself. And the 2D data adds more context to that 3D data, like overlaps, overlays, and blueprints. And they're again represented as line styles in different formats. So they add to the overall vertex count in the scene. Some perspective on the asset statistics, the sizes of these files can go somewhere between a couple of gigabytes to hundreds of gigabytes, depending upon the industry they come from. The polygon count can again go up to 1 billion. The mesh count can go up to a couple of millions. And what this directly translates from a technical standpoint is significantly high draw call count, immense input assembly and vertex shader pressure, and definitely VMM consumption. And this is what really translates to be our technical problem statement. Now, in the interest of time, I'll focus on what our strategy for solving this technical problem is, and less on how we might intend to solve loading of large AEC models. So we are using OpenUSD and Hydrographics interface as a cross-platform strategy, and we aim to equip OpenUSD with all the tools and techniques and solutions that we need that meet our rendering and visualization demands at Autodesk, including our technical problem statement with loading large AEC models. So we are using HGI Vulkan for Windows, Linux, and Android because, one, Vulkan gives us that cross-platform support that we need, that we have demand for, and two, we see value in leveraging greater control we get from these explicit APIs. Like Vulkan, and make use of that CPU and GPU access that we get. We're using HGI Metal for Mac OS and iOS, and HGI Web GPU for web-based platforms, HGI DirectX 12 for Windows, explicit Windows platforms. Both HGI Web GPU and HGI DirectX 12 have come from internal contributions and efforts at Autodesk and are currently in the process of getting merged into OpenUSD. Now, quickly talking about where we are in this journey of using Vulkan. Well, the current implementation, like Mauricio pointed out, the current implementation of HGI Vulkan on OpenUSD is neither complete nor stable, so we at Autodesk prioritize this and have completed the HGI Vulkan feature path for USD's base material pipeline, barring some caveats. We have disabled features like instancing, blending, drawing direct MSA to get here because they are currently broken. However, these are our known gaps, and we intend to resolve them immediately in our upcoming iterations. We have stabilized the Vulkan backend using industry standard tools and techniques, which I'll be quickly talking about in the next coming slide. Also, the current implementation of HGI Vulkan in OpenUSD uses OpenGL for presentation due to its simplicity. However, we see value in having a Vulkan-based swap chain management, composition layer, and a presentation infrastructure for the sake of stability and performance reasons. So it is currently owned by the application, this swap chain presentation and management layer, but we hope that in future this layer finds its way back into OpenUSD in some form. We currently have both the proposal and the implementation PRs of this effort in review to get merged into OpenUSD, and those are the links. So please feel free to go have a look at them and show some love. Leave your comments and reviews on that PR so we can follow up to progressing on this. The screenshot you're seeing to the right of that is basically a kitchen scene model rendered on OpenUSD with HGI Vulkan as a backend on Windows 10, running on an AMD CPU and an NVIDIA RTX discrete GPU. We see value in quickly progressing on Linux and Android as well. So we were able to successfully port this effort to Linux without any explicit platform changes. However, for Android, we successfully compiled all the subcomponents needed that USD has, and also addressed any challenges we had around packaging issues and the Android security implementations. So we have provided the specifics of that porting process in our proposal that is currently in review for OpenUSD's merge, and that is a link that we have provided. Also, the implementation PR for both these efforts for OpenUSD's merge will be coming in soon. That is implementation PRs for Linux and Android. And we are internally tracking them in terms of days. So once we go back from SIGGRAPH, this is one of the first things that we'll be working towards completing and documenting and pushing out. The screenshots that you're seeing on the right has been captured on an Ubuntu 22.04 operating system running on a AMD CPU and NVIDIA RTX GPU. And the screenshot to the right of that is being captured on a Galaxy Tab S8 Plus running on an Android 13 operating system. A little bit on debugging and tools. A good part of this journey was debugging for stability, and fortunately we were not flying blind. We relied on the Vulkan debug and validation layer for correct API usage across Windows, Linux, and Android. And shout out to OpenUSD for providing the debug marker infrastructure, so all our GPU resources were annotated. Now what that means is when we were using tools like RenderDoc and NVIDIA's Insight Graphics, these applications seamlessly hooked into our OpenUSD Stack Plus sandbox application and give plenty of perspective on the GPU side of things. We then relied on the debug markers that we saw on these traces for more context, and then went around resolving our GPU issues on the C++ side of things. Also, shout out to Lunar G for the Vulkan device simulation layer, among other layers as well. We intend to support a wide range of devices across different platforms, and we look forward to using this layer in simplifying our testing process. Finally, a little bit on community and collaboration. I'm very happy to be here and share this progress with all of you. This is also an opportunity for me to reach out for collaboration and contribution from the open source communities we have here, both from OpenUSD and the Kronos Working Group. So please do take time out of your schedule and show us more love and follow up to these PRs with us. I hope we're able to continue this conversation outside of SIGGRAPH as well. So you can reach us at the Autodesk Graphics Platform team, which is at agp@usd.com. And also, you can have OpenUSD, Hydra, and Vulkan specific implementation questions and conversations on aousd.org. Please feel to participate there. We do keep an eye out for our queries. Thank you. This is a capture on Windows operating system running the USD stack with Hydra, Vulkan on Hydra. And this is what we have on Android of the same implementation of the other port. Thank you.
Hi everyone, my name is Jasmin. I'm a software development manager at Autodesk in the Flame team. First of all, I want to thank Tim Lewis, Marty Johnson, and Lizzie Hartson for reaching out to us and giving us this great opportunity today to talk about one of the biggest undertakings in the Flame history, which was to port Flame from legacy OpenGL to Vulkan. So super excited to be here. And I also want to send a shout out to the Flame team, which are currently looking from Montreal, and especially the 4 main contributors in this project, which are Jasmin Frenette, Samuel Falardeau, Bernie Isma, and Fabrice Lefebvre. Yeah, safe harbor statement, so I will be giving some insights at the end of this project, so obviously plans can change. Presentation agenda, so I'll be giving a quick overview of Flame, so I'm not sure everyone here knows what Flame is all about. Then I'll be talking about the project conversion strategies that we used, some technical challenges that we had and solutions, and finally the project outcome. So what is Flame? Hopefully the video is going to work. Awesome. So Flame is a timeline-based visual effects and finishing solution. It has a proprietary 3D engine that is used mainly for real-time and visual effects. It is used in commercials, TV episodics, and features. It has a very powerful machine learning engine which is used to assist artists in creative tasks. And I'm really proud to say that Flame is used around the world by high-end studios and artists that rely on its performance, its rendering quality, and its feature set. And also, although this video shows some capabilities in Flame, you need to understand that the feature set in Flame is huge. So we have very complex workflows, we have multiple components, and we connect with third parties like Substance and OpenFX. So that being said, our code base is very big, and it's been relying on legacy OpenGL for over a decade now. So you can appreciate the fact that porting a software like this to a more modern graphics API can be really challenging. So on that note, talking about challenges, so obviously a huge feature set. Flame is also supported on Linux and the Mac platform, so Intel and Apple Silicon, so we have to keep that in mind. When we started the project, we knew this was going to be a multi-year project. So obviously you have to plan accordingly. And finally, one of the biggest challenges we had was memory management. So obviously in Vulkan, we all have to, we're responsible for the memory manager, right? So this was something new for us, coming from a legacy OpenGL. And so we've been tweaking our memory manager for multiple years until the very end of our project. So I won't be talking about memory management today because it would take about 500 slides, but some strategies I can talk about. Molten VK. So I can safely say that Molten VK was key to success to this project. For us, it was unacceptable to have to maintain 2 graphics API implementations at the same time, so Metal and Vulkan. So knowing that there was a solution for Vulkan on the Mac was key for us. We knew there was a risk because we weren't certain about the overhead of Molten VK. But it turned out in the end that we've seen up to 50% speed increases on the Mac. So it's safe to say that it was a great solution. And also the feature set for Molten VK, I mean, we've never had any issues with features missing whatsoever, so that was great for us. Also abstraction layers, so I'll be talking about this in a few slides. Master branch, so if you're working on multi-year projects, obviously, if you can avoid branching out, that is also very important. And finally, iterative and automation-driven approach. So what I mean by that is, thanks to the Vulkan interrupt extensions, we were able to use interrupt with OpenGL and Vulkan and convert components by component. So for example, in this processing pipeline, we could take AI tools and convert them to Vulkan and still have like mainly OpenGL modules and processing nodes inside Flame, and it would all work correctly. And the advantage of that is that we were able to take advantage of our 20,000 plus daily automation tests that we run from day one, right? So that was perfect for our project. So a first technical challenge that I can talk about today, Matchbox. So what is Matchbox? Matchbox is a feature in Flame that allows artists to create their own creative tools by writing their own shaders. The problem with Matchbox is that it's been around for a very long time, and artists have been writing legacy GLSL code, right? So we can't go from legacy GLSL to SPIR-V right away. So what we did is we created our own runtime shader converter, pretty simple. So basically cleans up the shader, it packages all the uniforms together, fixes the keywords, and then we're able to compile this using GLS Lang to SPIR-V. Another technical challenge, so we all know that writing Vulkan code can be quite more difficult than OpenGL, so like we mentioned before. So what we did to streamline the whole conversion process is create an abstraction layer, which basically contain multiple tools to help developers try to accelerate the conversion process. So the advantage of doing this is that we were able to distribute the work between multiple developers throughout the years, right? So we could have developers join the team temporarily for a few months just to help out with some components. And it was easy for them to learn Vulkan, first of all, because we had this abstraction and these tools. So for example, one of these tools that we created is the shader configurator. So it basically uses shader reflection. So if you want to set a uniform by name, it was super easy. So basically the configurator will find the correct offset in the buffer to set the uniform value for you. So this really reduces the amount of lines of code you need at the end. And finally, another technical challenge we had, the fact that in this project we had so many components in Flame that we had to convert to Vulkan. So we wanted to concentrate on the more critical aspects of Flame, right? Everything that affects render quality, performance. And we didn't want to waste too much time with UI, overlays, and diagnostic tools. So what we did is an OpenGL translation layer. So we created this wrapper around the OpenGL API, which basically tracks the whole state. So when these tools need to render or draw, it basically translates and commits all of the state into actual Vulkan pipelines and comments. Obviously, you cannot optimize that much when you use this, but so you use these things only for the non-critical components, and that's exactly what we did, and we concentrate on the really critical stuff. So unfortunately, I cannot show any benchmarks today for so many reasons. I would have loved to. But I can safely say that we run hundreds of performance benchmarks every single day. And we've seen performance gains across the board on Linux, on Mac Intel, on Apple Silicon. And I can share with you some artist testimonials which have installed our latest version of Flame, which is Flame 2024 Update 1, which contains Vulkan. And some of our clients are seeing up to 50% faster rendering times on the Mac through Molten VK. So the project outcome, so basically performance improvements, obviously, better memory management and stability due to, and thanks to Vulkan for giving us all this control on memory management, and obviously successful Flame 2024 Update 1 in the end. So although we're seeing performance gains today with current configurations, we do believe Flame is at a performance point of inflection right now where we're seeing all of these new CPUs, GPU capabilities coming up, and we feel it's all coming together with our Flame conversion that we've done, and it's going to give our Flame artists just a better performance experience in the end. But there is so much more we need to do, and this is where I'm really excited, because with Vulkan, there's many things that we couldn't really do in the past with legacy OpenGL. So, for example, I'm talking about Vulkan subpasses, which is something we didn't really have the time to use, but definitely we can use this. Multi-threaded processing pipeline, a lot harder with legacy OpenGL. With Vulkan, I do believe it's going to be a lot easier. Multi-GPU support. And lastly, moving all of our OpenCL to CUDA and CUDA to Vulkan Compute, which would be pretty easy. So that's pretty much it. Thank you.
Yeah, we will be around later for questions. In the interest of time, we're going to turn it, that's all from Autodesk. We're going to turn it over to Hai, who's going to talk about the promised basic ray trace debugging in Vulkan. I want to know about this.
You might be disappointed because you're too advanced. I actually started my career supporting Flame in visual effects, so it's very fitting that I follow a Flame talk. Okay, so in the interest of time, I'm going to skip a section of this. It's a wall of text anyway. You can download the slides and read it. But unfortunately, it's an important section. Hopefully, I can do like a web version of it at some point. So a little bit about me. My name is Hai. I am a graphics lead for XR at Google. I previously worked on Stadia. I contribute to DXC and Sphere Reflect. Like many of you, I love computer graphics, and thank you for being here. And I know I'm the barrier between you and beer, so I'll try to make this quick. Okay, so a bit of background about this talk. I don't remember when I started doing GPU ray tracing, but I got really bored one day, and I had a lot of free time, so I just started mooking around with the Vulkan API and Directory 12. And the first thing I wrote was I wanted to see the coordinate system to prove to myself like how ray generation would work. And I wanted to see some consistency between Vulkan and D312, and voila, it's the same thing. Anyway, I went from this to this in about 2 months, and had a lot of help along the way. And it was during my evenings and weekends and holidays, because what else you can do with your spare time but write graphics code? And so there was a lot of debugging involved, and I want to share some of the things I learned along the way to help me solve some of these problems, because debugging ray tracing is hard. Okay, so this is what we're going to talk really quickly about today. The target audience for this talk is anybody who's new to Vulkan ray tracing, and this talk primarily focuses on the API side. We'll get a little bit into debugging pixels, the assumption is that you're somewhat familiar with the Vulkan ray tracing concepts. Thank you, Autodesk, for talking about some of that, because I wouldn't have time to. Mainly acceleration structure, shaders, and pipelines. Also going to assume that you're familiar with Vulkan descriptors and resources. And the focus of the API that we're going to look into is VKCMD trace rays. Unfortunately, we don't have time to go into things like BLAS and TLAS debugging. I do have some comments about that. Like normal graphics, we can categorize ray tracing debugging into 2 areas. The first one is debugging the API, and obviously the second one is debugging rendered pixels. And while each one of these has they're vastly different, but you kind of approach in the same way from a basic level. So you might be wondering some of these things. For what tools can I use? Show me what's happening in the API, or sorry, my app. What's the pipeline shader configuration? Can I do with my shaders? What are some useful tidbits for me to keep in mind while I'm debugging like rendered pixels? Can I examine the pixel values? Can I see how Vulkan interpreted my scene? And can I graphics printf, because when you lack all other tools, there's always printf. Okay, so this is, sorry. So first up, we'll look at what tool can I use. The unfortunate news is that RenderDoc does not support Vulkan ray tracing. So if you try to launch an app with it, it will just fail. I don't know if or when their ray tracing support is coming, but there is a tool that works, and it's Insight Graphics. So the next few examples are going to use Insight. So this might look like an ad for NVIDIA Insight, but it's not. It's maybe a little bit of a tutorial. Definitely not a sponsored talk by NVIDIA that was on Sunday at the expo, if you missed that. So Insight was the only debugging tool that I found that worked for me, and hopefully after this little tutorial, it can help you if you're running into problems with Vulkan ray tracing. Okay, so this is the, this is the Insight screenshots over the next few slides are going to be a capture of this scene. And if you're not familiar with this, this is a Sphere Flake by one of the OGs of computer graphics, Eric Haynes, who might be wandering around. I'm not sure if he's here. But a little bit about the scene. There is 1 ray gen shader, 2 mist shaders, 2 shaders in the hit group, and 3 resources that it touches, acceleration structure, output image, and buffers. Max recursion is set to 5, and there's 66,000 something odd spheres. And pretty much when I was learning ray tracing, every scene had, or every example I saw had sphere flake, so I thought I'd include it to show everybody else. Okay, so if you haven't seen Insight Graphics, here's what it looks like. It looks pretty much like any other graphics debugger. There's a bunch of different components on here. There's a timeline, events viewer, API inspector, and an object browser and a resource viewer that will pop up when you start drilling down on the details. So let's take a close look at some of these. So this is where debugging generally starts. You look at the events list or the events timeline, and you start drilling down on whatever Vulkan command you're interested in, right? So in our case, we want to look at event 17, since it's the call to VK CMD trace race. So if you don't remember what that looks like from the API side, here's what it looks like. You know, one of the beautiful things about debuggers is that it helps you consolidate a lot of the calls into a small piece of information that you can look at. But you know, for VKMD trace arrays, the things that you pass to it are the SBTs and the image and width and height, and hopefully you set the right pipeline and the right resources before that in the descriptors. So from the debugger perspective, this is what it looks like. You see the values that are passed into the parameter, you can inspect them. You know, so if you need to check your stride and size for the SBTs, here's where you can do it. Also, you can make sure that the device address isn't null for the buffers that you're passing in for the SBTs. You know, if you're getting that dreaded black screen, it's also another place you can look, because if you have like incorrectly configured SBTs, that might be a result. Also, I believe that the validation layer should catch any egregious errors that you make with this level, at this level of the API. There are parts that it can't, and we'll talk a little bit about that. So moving into the API inspector, and this is where the good stuff is. Here we can see the pipelines, the SBTs, the descriptors for the resources, and this pipeline that we're looking at is a GLSL based pipeline, so all the entry points are main. But what's nice here is that you can see what ray tracing groups are referencing which shaders. So if you need to find, you know, if you need to figure out if like your pipeline was misconfigured or not, this is a great place to see it. It's a little bit easier than looking through the code. You know, I've actually gotten a few things wrong before, and Insight definitely helped me find it. So the descriptor layout foldout shows you the resources that are used by the pipeline. I do wish that it also listed the actual names of the variables that are from the shader using reflection. The other thing that I think is missing is I wish max recursion depth was also visible from here, but it's not. You know, but it's not a big deal. You can get to it by just clicking on the pipeline. It's just a matter of convenience. So this is a HLSL version of a pipeline. Hopefully the screenshots are not too blurry. Apologize. Not a whole lot of room on these slides. So it's pretty much the same thing as the GLSL version, but you get more descriptive entry point names. You know, it's a little bit more helpful if you're trying to track down exactly which shader you're looking for. So the thing about was when I was taking a screenshot, I actually found an error or a bug in one of our samples. And this one, it was descriptor binding 12, it has combined image sampler and descriptor types. And that's actually wrong, because while you can do combined image sampler in HLSL with Vulkan, it's actually really not easy. And in our samples, we definitely don't use it. So thanks to Insight, we actually found and fixed this while we were making these slides. So diving into the first shader stage for the pipeline, the shader stage, like most of these shader stage tabs will contain like the shader module, the resources. This stage does not use any shader records, so we don't have any of that here. We'll look at that in just a bit. And you can actually view the source code to the shader by clicking on the address for the shader module, and we'll cover that a little bit too. But here's, you can click on the image view, the output image, and you can see the results of the VK-CMD trace race calls. The other thing is that for the Vulkan version, there's the absence of the acceleration structure. I'm not quite sure where that is. It's definitely in the D3D12 mode. Next stage, and here this is the MIST shaders, and since it's a really simple example, it only shows the shader modules, and we just have our two only MIST shaders here. And lastly, this is a hit shader group. and we finally have some access to the shader records. And the purpose of the sample the purpose of the SphereFlake sample was to actually show a resource passed via the shader records, which is the buffer for for SphereFlake. And here you can click on the address for the buffer and see the resources, or sorry, see the actual data. But for some reason in the version of Insight that I'm using, it interprets the size as 64 bytes, which is the size of the buffer address. And so you just end up seeing like the first two elements. So before moving on, one of the things that would be really useful to see in these panels, if NVIDIA is listening, is that the shader entry points. You know, like the first, if it's like one or two shaders, you could probably figure out which one you're looking at, but you start having like 6 or 7, a little bit harder to track. Okay. So I mentioned earlier that you can click on the shader modules and look at the source code. So when you do that, you get your choice of SphereV or GLSL. I couldn't get the HLSL cross-compile to work. That might have been my shader. Anyway, regardless of what the original source is based off, if you can look at the GLSL, you can probably figure out which shader you're looking at and maybe even spot like whatever bug you're looking for. Obviously, if it's like the wrong shader, you're going to get wrong results. So this is a pretty cool feature that I kind of found by mistake. So like other graphics debuggers, you can edit and compile and promote the shaders. Promote is the Insight lingo for rebuilding the pipeline so that you can use your newly edited and compiled shaders. And in this small example, I just changed the background color from the blue gradient that it only has to this yellow. And this worked right away. I didn't have to relaunch my program. I just had to like move the scrubber back and forth. And so this is really useful if you are, if you want to make a quick change to your shader to test like some debugging. Okay, so let's talk a quick bit about debugging rendered pixels. So when you start debugging pixels, you've crossed over into shader territory, which means that there's going to be some math involved. And there's some basic things that you want to keep in mind when you're debugging. Turn on the validation layers, obviously, but one of the things about debugging graphics is that like when you are in the thick of it and your brain begins to get a little mushy, you might start questioning like, what coordinate system am I in? Like, is the math I'm doing correct? So it's pretty helpful to just note some of the conventions that you're using, particularly in ray tracing, since like the coordinate systems are whatever you choose. So the other thing to keep in mind if you're doing recursive ray tracing is that the only vendor that currently supports recursive ray tracing is NVIDIA. I found this out the hard way. I should have just looked at the properties. But, and also, lastly, just remember that this is real-time ray tracing. You can add like whatever debug UI you want to make it easier. Like you get instant feedback. It's kind of weird because with ray tracing we associate with having to wait for results, but we don't. It's real-time. Okay. So going back to the questions, can I examine my pixel values? Yes, Insight has a graphical viewer that lets you very easily examine your pixel values. And you can also do isolate channels. So you can examine the pixel values as float or hex integer. I couldn't find a setting to change it to decimal integer, so if you're interested in that, you might have to do some quick math between hex and decimal. There's also a memory viewer, and here you can select between an address or index for the axis, but I'm not positive. I'm sure there's a good use for this, but I think for me it would have been easier if these were pixel coordinates so I can find the pixel I'm looking at a little bit easier. But you can do some quick math if you have your image dimensions and figure out like what the index is. But keep your calculator handy if you're going to do that. And lastly, if you don't have access to Insight and you can add a debug UI using IMGUI. Brad was nice enough to just take one of our samples and add a really quick UI using IMGUI to do this. It lets you lets you examine the pixel values because graphics debugging you might want to write something fun and fancy to the frame buffer so you can debug it. So one of the things that one of the things that you might want to know is, can Vulkan show me how it interpreted the scene that I handed it to while I'm ray tracing? And before we go on to that, I went to the NVIDIA talk on Sunday, and I saw the pro version of Insight, and so I know this is possible in Vulkan, but it is not possible in the version of Insight that you download as a consumer. But it's unfortunate because this is really useful to have, and here's a screenshot of the D3012 acceleration structure viewer. So this is immensely helpful if you want to debug geometry and procedurals, geometry that's triangles or procedurals. One of the hardest things is sometimes you question if you configure your geometry correctly. And a tool like this can, if you misconfigured it, probably just end up scrambled, or you might get a crash. But anyway, if you don't have a visual acceleration structure viewer, you can always graphics printf. In our case, it's ray tracing printf. And so the very fundamental version of this is just coloring one color for your hits and a different color for your misses. Here's a very simple shader or two simple shaders, one for closest hit and one for miss, and one of them just colors it red, and one incorrectly colors it as black. It should be red. My apologies, I'll fix that. So if you need to see some separation in the geometry with graphics printf, then you can just do something like write out the barycentric coordinates, or you can use world hit position or object ID or primitive ID or instance ID. Those take a little bit more math because you start writing those values out, it's going to probably overload some of the values. But anyways, printf, it's there. You can, if you have access, if you have your geometry data pumped in, you can always write geometry data as well. So normals, text chords, tangents, all the things that you would normally have associated with a render. So I found that it's super handy to keep just a text file of these shaders, and I can just copy them in and replace them when I'm starting to question whether I messed up in the shader or not. It just helps me get it back to fundamentals really quick, and then it can work forward. But here's a list of ready-to-go printf shaders that I'd recommend. If you need to have something ready to go. And so it's also helpful sometimes to just get a second opinion if you have code that's written that is easily portable to a different API like D3012. We had a case where this is obviously a really simple example, but the top image is Vulkan, the bottom image is D312, and we noticed that the top red cube looked a little bit off, and Brad tracked this down to it being a bug in both the shader and the API on the Vulkan side. The shader, the bug in the shader was for both APIs, but Direct3D12 for some reason was a lot more forgiving about how it handled missing resources, or sorry, underspecified resources. So there's this entire section about debugging crashes. I'm going to skip it, but I'll just show you the slides real quick. But debugging crashes is you get to think really hard, and it's unfortunate, but that's the way it is. But again, you want to break it into two different categories. Crashes before you trace rays and crashes while you're tracing rays. There's 4 walls of text that you can read once you download the slides, and basically it's just steps on walking through the API and checking the critical fields that you would when you're trying to track down a crash. One thing I do want to say about tracking a crash while you're ray tracing is that there are, I work on DXE a little bit, and while there is, generally, when you get a crash, it's probably not a compiler bug, but there is a greater than 0% chance that it might be. So if you suspect that there is a shader compiler bug, well, the best way to approach that is It's just to comment out the code and then reintroduce it until you find the source of the problem. And then file a bug on our GitHub so we can track it down and fix it. If you're going to do that, though, whatever resources that you're using, you need to read from it and then write to it either in the payload or write to it directly out to a resource. The reason why you want to do that is if you don't touch a resource, the compiler's dead code elimination will just yank it out, so you'll never see it. So keep that in mind if you're going to use the, if you think you suspect a shader bug, a shader compiler bug, but it's highly unlikely. The other thing is, if you are set up to go with NVIDIA's Aftermath, I saw some really cool demos of it on Sunday as well. It seems really helpful. Unfortunately, I haven't had the time to track it down yet, but I definitely recommend that you do if you're running into crashes. Sorry, NVIDIA, I have some feedback about Insight. If you're watching, this would be really useful, not just for me, but I think for everybody else too. And like I said, I saw the pro version on Sunday at the expo, and so I know what like glorious ray tracing debugging can look like. Just a plea from the random guys on the internet who are doing ray tracing as a hobby. Okay, so that's pretty much the end of my talk. There's some folks that I want to thank for helping me get to this this ray tracing journey. And here's the link to Eric's SphereFlake, original SphereFlake. And also, I didn't get to mention it, but Will Usher has a really awesome blog about SBTs, and there is a tool or a little toy app that he has on the web that allows you to just like visualize what the SBT looks like. And also, you can insert shader records and whatnot until you get an idea of what the stratum size looks like. Additionally, all the sample images that we use is available on my graphics experiments GitHub. And it's just a collection of graphic samples that are done from like a hobbyist point of view. And it's in Vulkan, D3D12, and Metal. And the whole point of this project is just to have fun with computer graphics. And the ray tracing portion just walks you through the entire thing from UV coordinate generation all the way to a progressive real-time photoreal-based path tracer. And that's it for me, and I think everybody probably wants to grab a cold beer.